Hi, today I am going to talk about GPS. What is GPS? GPS Global Positioning System is a network of satellites orbiting the Earth that provide location information to GPS receivers on the ground. It allows devices to determine their precise location, velocity, and time, enabling navigation, tracking, and mapping capabilities worldwide. Here I am going to give an overview on GPS structure, GPS function, how GPS works, GPS applications, GPS signal structure, GPS error sources, GPS augmentation systems, and GPS modernization. GPS structure. Constellation of 24 to 32 satellites orbiting Earth consists of 3 segments. 1. Space segment. 24 to 32 operational satellites in medium Earth orbit MEO. Satellites are equipped with atomic clocks for precise timing, transponders for transmitting GPS signals, solar panels, and batteries for power. GPS satellite constellation. 6 orbital planes, each with 4 to 6 satellites. Satellites are replaced every 10 to 15 years and spare satellites are kept in orbit as backups. 2. Control segment. Master Control Station NCS in Colorado, USA. Multiple ground antenna stations worldwide. Monitoring and control of satellite health and signal quality. Prediction of satellite orbits and clock behavior. 3. User segment. GPS receivers and user devices. Various types of receivers, including handheld receivers, vehicle-mounted receivers, aviation receivers, maritime receivers, user devices, such as smartphones and tablets, with integrated GPS capabilities. GPS functions. GPS functions are 1. Navigation. Location determination, latitude, longitude, altitude. 2. Velocity calculation, speed and direction. 3. Time synchronization, accurate timing. 4. Tracking. Vehicle tracking, fleet management, logistics. 5. Asset tracking, packages, containers, equipment. 6. People tracking, emergency services, location sharing. 7. Mapping and surveying. Geodetic surveying, precise location and elevation, and mapping and charting, topographic, hydrographic. Now I am going to give an overview on how GPS works. 1. GPS signal transmission. Satellites transmit radio signals containing location data, ephemeris, timestamp, accurate to nanoseconds, pseudorandom code C, or PY. Signals transmitted on L1 1575.42 MHz and L2 1227.60 MHz frequencies. 2. GPS signal reception. GPS receiver detects signals from multiple satellites, minimum for required for 3D location. 3. Receiver measures time delay between signal transmission and reception, time of arrival. Frequency shift, Doppler effect due to satellite motion. 4. Receiver uses measurements to calculate pseudo-range distance from satellite to receiver. Doppler shift velocity component along line of sight. 5. Trilateration. Receiver uses pseudo-ranges and Doppler shifts from multiple satellites to calculate location, latitude, longitude, altitude, velocity, speed, and direction, time accurate to nanoseconds. 6. GPS algorithm. Receiver uses complex algorithms to correct for satellite clock errors and ephemeris errors, compensate for atmospheric delays, ionospheric and tropospheric, solve for location, velocity, and time using least squares method. 7. DGPS and augmentation systems. Differential GPS. DGPS uses additional signals from ground stations to improve accuracy. Wide Area Augmentation System was an European geostationary navigation overlay system. EGNOS provide additional correction data. GPS applications. 1. Aviation. GPS is used in aircraft navigation, approach, and landing. It enables pilots to navigate accurately and safely, even in low visibility conditions. 2. Maritime. GPS is used in navigation, tracking, and route planning for ships, boats, and other vessels. It helps prevent collisions and improve safety at sea. 3. Land surveying. GPS is used to determine precise locations and boundaries for mapping, property surveys, and geodetic applications. 4. Emergency response. GPS is used to locate emergency services, such as ambulances, fire trucks, and police cars, and to guide them to the scene. 5. Fleet management. GPS is used to track and manage vehicle fleets, improving efficiency, reducing costs, and enhancing customer service. 6. Geocaching. GPS is used for recreational purposes, such as geocaching, a game where players use GPS coordinates to find hidden containers. 7. Agriculture. GPS is used for precision agriculture, guiding farm equipment, and optimizing crop yields. 8. Construction. GPS is used for site surveying, machine guidance, and asset tracking, improving construction efficiency and accuracy. 9. Environmental monitoring. GPS is used to track and monitor environmental phenomena, such as wildlife migration patterns, ocean currents, and climate change. 10. Consumer electronics. GPS is used in smartphones, smartwatches, and other devices for navigation, tracking, and location-based services. 11. Autonomous vehicles. GPS is used in self-driving cars and drones to enable autonomous navigation and decision-making. 12. Timing and synchronization. GPS is used as a reference clock for synchronizing telecommunications networks, financial transactions, and scientific research. 13. Geophysics and geology. GPS is used to study plate tectonics, earthquakes, and volcanic activity, and to monitor groundwater levels and soil moisture. 14. Weather forecasting. GPS is used to track atmospheric conditions, such as temperature, humidity, and pressure, to improve weather forecasting. 15. Space exploration. GPS is used in space missions for navigation, orbit determination, and timing. Here is information about GPS signal structure. L1 frequency 1575.42 MHz. C. A code course acquisition code PY code precise code, navigation data ephemeris, almanac, etc. L2 frequency 1227.60 MHz. PY code precise code, navigation data ephemeris, almanac, etc. Signal components. Carrier wave sinusoidal wave at L1 or L2 frequency. Modulation spread spectrum technique. Pseudorandom code C, A or PY code. Navigation data superimposed on the pseudorandom code. C, a code. The C, a code is also a particular series of ones and zeros, but the rate at which it is generated is 10 times slower than the PY code. The C, a code rate is 1.023 million bits per second. Here, satellite identification is quite straightforward. Not only does each GPS satellite broadcast its own completely unique 1023-bit C, a code, it repeats its C, a code every millisecond. The legacy C, a code is broadcast on L1 only. It used to be the only civilian GPS code, but no longer. It has been joined by a new civilian signal known as L2C that is carried on L2. The C, a code is used for civilian GPS use, while the PY code is reserved for military and precise applications. GPS error sources. GPS error sources are 1. Satellite clock errors. Satellites' atomic clocks can drift or bias, affecting signal timing, error, up to 1.5 meters. 2. Ephemeris errors. Satellite position and velocity data ephemeris can be inaccurate, error, up to 1 meter. 3. Multipath interference. Signals reflected off nearby surfaces, causing multiple signal paths, error, up to 1 meter. 4. Atmospheric delays. Ionospheric and tropospheric delays affect signal propagation, error, up to 10 meters. 5. Receiver noise and bias. Thermal noise and bias in the receiver's electronics, error, up to 0.5 meters. 6. Satellite geometry. Poor satellite geometry can weaken signal strength and accuracy, error, up to 1 meter. 7. Signal obstruction. Signals blocked or attenuated by obstacles, buildings, trees, etc., error, up to 10 meters. 8. Orbit and clock prediction errors. Inaccurate predictions of satellite orbits and clock behavior, error, up to 1 meter. 9. Systematic errors. Biases in the GPS system, such as satellite and receiver instrumental biases, error, up to 1 meter. These error sources can combine to affect the overall accuracy of GPS positioning. However, advancements in technology and correction techniques have mitigated many of these errors, enabling GPS to achieve high accuracy and reliability. GPS augmentation systems. GPS augmentation systems are 1. Wide Area Augmentation System WAAS, developed by the U.S. Federal Aviation Administration FAA, uses a network of ground stations to provide correction data, improves GPS accuracy to 1 to 2 meters, used for aviation, maritime, and land applications. 2. European Geostationary Navigation Overlay System EGNOS, developed by the European Union, similar to WAAS, with a network of ground stations, improves GPS accuracy to 1 to 2 meters, used for aviation, maritime, and land applications. 3. Differential GPS DGPS, uses a network of ground stations to provide correction data, improves GPS accuracy to 1 to 10 centimeters, used for precision applications like surveying, mapping, and agriculture. 4. Ground-Based Augmentation System GBAS, uses a network of ground stations to provide correction data, improves GPS accuracy to 1 to 2 meters, used for aviation, maritime, and land applications. 5. Satellite-Based Augmentation System SBAS, uses additional satellites to provide correction data, improves GPS accuracy to 1 to 2 meters, used for aviation, maritime, and land applications. These augmentation systems improve GPS accuracy and reliability by providing correction data to compensate for various error sources. They enhance GPS performance for various applications, including aviation, maritime, land surveying, precision agriculture, and more. GPS modernization. 1. GPS-3 satellites. New generation of satellites with improved signals and accuracy, designed to replace existing GPS satellites. First launch in 2018, with ongoing deployments. 2. L1C signal. New civilian signal with improved accuracy and compatibility, designed for international use and interoperability. Initial deployment on GPS-3 satellites. 3. L5 signal. New signal for aviation and other high-precision applications, operates on a different frequency, 1192.79 MHz, provides improved accuracy and robustness. 4. M-code signal. New military signal with enhanced security and accuracy, designed for military and government use. Initial deployment on GPS-3 satellites. 5. OCX Operational Control System. New ground control system for GPS-3 satellites, improves signal accuracy, reliability, and security that enables more efficient satellite operations. 6. GPS-3 follow-on GPS IIF. Next generation satellites, with further improvements, focus on signal accuracy, security, and adaptability, planned for launch in the mid-2020s. GPS modernization aims to enhance the system's accuracy, availability, and security for various user communities, including civilian, aviation, and military applications. The new signals and satellites will provide better performance and compatibility, while the OCX system will improve ground operations. The ongoing modernization efforts will ensure GPS remains a reliable and vital component of global navigation and timing infrastructure. For more informative videos, like and subscribe to our channel, TP Info.